Hello, we're Team 33, and this group consists of Nicolas Handoko,
Alina Liu.
Tran.
And Diana Quach.
For our project, we perform a structural analysis on a medical field hospital tent.
With the COVID-19 pandemic still going strong after a year, there is a dire need for speedy vaccination. There is a clear lack of mass vaccination facilities, with hospitals still being the primary location for administering vaccines. In order to speed up vaccination, a wider distribution of vaccination facilities must be opened up. For our project, we propose the development of a medical field hospital tent that is portable, durable, easy to set up, and to take down. This photo shows a current COVID-19 vaccination site in Los Angeles, similar to the medical tent that we're designing.
To assist in the effective and efficient distribution of vaccines to help finally bring the pandemic to an end, it is important for medical workers to have access to a medical tent that is both light enough to be easily transportable and simple enough to be quickly set up and be taken down. In addition, the tent must be durable enough to withstand stresses and strains caused by the weight of a tarp to protect patients from the elements. Any equipment that may need to be hung from the truss, such as lights, and various weather conditions such as strong winds and rain. This is important especially in locations recently struck by disasters like hurricanes, tsunamis, and earthquakes.
The structure consists of 25 aluminum rods and 12 connectors assembled together into a truss. To ensure that our tent truss system is simple enough to efficiently manufacture and quickly be set up by health workers, we designed it so that it only consists of 3 different component types: 25 4-centimeter diameter, 3-meter long circular beams, 6 3-way connector parts, and 6 4-way connector parts. The diameter of the beams will be adjusted accordingly after mass minimalization calculations. All parts are made of aluminum 1060 alloy.
The final length of the tent will be 9 meters strong, consisting of three of the rods. It will be 5.2 meters wide, as well as 4.5 meters high, a relatively large tent compared to the many other medical field hospital tents. This allows for the tent to accommodate a large amount of patients and health workers, while also allowing for proper social distancing measures to be maintained. The SolidWorks diagram shows the dimensions of one section of the side view of the tent.
2 light fixtures to illuminate the tent will be hung from the 2 4-way connector parts circled in the illustration, with each light weighing 0.7 kilograms. In addition, the tent will be covered by a polyethylene-coated nylon tarp weighing 5 kilograms. We chose this tarp material because it is both durable and waterproof without being too heavy.
In addition to the weight of the light fixtures and tarp, we will calculate the stresses and strains caused by weather conditions such as winds. Depending on the wind speed, the force can be calculated over the tarp's area. At the joints of the truss, the displacements can be found and used to find the stiffness matrix of the entire system. The structural analysis will consist of finding the stiffness matrix for a cross-section frame of the medical tent. The external forces that will be included are the weights from the light fixture and the distributed loads of both the tarp and the wind blowing in a horizontal direction. These can be condensed into point forces at the center of the area that they are acting on, as shown in the drawing.
The force exerted due to the weight of the tarp as a point force is calculated to be 49.05 newtons. As for the force due to the weight of the light, it is 6.867 newtons. The force of the wind can be calculated with the product of the area of the cross-section, the density of the wind, and the speed of the wind. The cross-section is 9 square meters. The density of air at sea level and room temperature is 1.229 kilograms per meters cubed. And the average wind speed in California is 7 miles per hour, which is roughly 3.129 meters per second. With the given parameters, the average force of the wind exerted on our tent would be 108.02 newtons.
The truss system will be affected by compression and tension, meaning that we will have to account for failure criterions of yielding, buckling, deflection, and stiffness. Since the tense joints are fixed, the K value is equal to 1 when calculating for the buckling equation. For the factor of safety, we have to consider our given parameters. With our chosen material of aluminum 1060 alloy, the properties are 69 gigapascals for the Young's modulus, a tensile strength of 68.9 megapascals, and a yield strength of 27.6 megapascals. This is considered to be a reliable material. We came to the conclusion of a factor of safety of 1.5 given that the weather conditions are not severe. The equations are necessary to calculate each of these criterions are shown on the slide.
To ensure easy transport and setup of the tent, especially in time-urgent medical situations, we will calculate the absolute minimum mass that the structure can be and not be affected negatively. It will also be able to withstand a given load and maintain its structural integrity. We can also find the critical lengths of the design to prevent buckling and improve safety.
At the current time, our team is currently still in the process of calculating the failure criteria for our truss system in order to calculate the minimum mass. We can use this result to find the minimum diameter needed for the beams of the tent. The beams itself the cross sections are a circle. We will edit our design accordingly with the new calculated value.
As for results, we have no results. We are in the process of finalizing our mathematical analysis. We have finished the SOLIDWORKS CAD model of the tent, as can be seen in the previous images. Here is a preview of our current progress with the stiffness matrix of member 2-3 of our structure.
With a sturdy and lightweight medical tent, disaster medics will have a much easier time transporting and setting it up. This then leaves more time for them to focus on patients and their work. We hope to provide a well-designed structure for this purpose. Thank you for watching our project presentation.